These data values of 0, 1, 2, 1, returning to 0, 1, 2, 1, give a sawtooth waveform of a very specific period of 4 units. We can use this to investigate the technique of autocorrelation. Identifying data as the variable, we select to display autocorrelations and partial autocorrelation. We will also click on Options, and under Options we will choose to select 10 lags in the autocorrelation analysis. So we click Continue and click OK. The autocorrelation function ACF shows strong positive correlation when the lag number is equal to a specific multiple of the period of the waveform. So we see positive correlation after 4 units and after 8 units. And we see negative correlation in the half periods, so after 2 units, 6 units and 10 units. So this waveform is producing strong signals at every half period. If we now look at the partial autocorrelation, we see the strong negative correlation after 2 units, that is just half of the waveform period, and the other signals have been suppressed. If we apply the same analysis to the numbers of porpoise sightings every 3 months, so that 4 units here represents 1 year, we will use autocorrelations first, the data, and again, where the period of the initial data was 4 units represented 1 year, we see a significant correlation with the number of sightings with the number of years, but we are unable to pick up any other specific variation. However, if we now look at the partial autocorrelation, we see the very significant negative correlation after 2 time units, i.e. for half a year, but we've also picked up the possibility of another variation giving a negative correlation after 6 time units, which would represent a period of oscillation of 12 units corresponding to 12 quarters or every 3 years. We can further investigate this by using spectral analysis on this data. So we select spectral analysis and we will record this by period. Click OK. So what we see is this curve, which plots the strength of any frequency component as the period of that component. And on this axis, this is 1E1, which represents a period of 10, 20, 30, 40. The period of 1 year in the oscillation would be a period of 4 units, which is represented by this peak here. But we also identify this other broad response corresponding approximately to the period of 12 units or 3 years that we identified in the partial autocorrelation. We can now consider the same analysis using Minitab. The data in column C1 of 0, 1, 2, 1 returning to 0 and then repeating the same pattern with a period of 4 units represents a very distinct sawtooth waveform, and we can use this to investigate the use of autocorrelation in Minitab, for which we go to Stat, Time Series, Autocorrelation. We will select the sawtooth waveform and we will specify 10 lags within our analysis and then run the analysis. In this output, the autocorrelation function shows strong positive correlation after 4 lags, which represents one complete period of the sawtooth waveform. And then it shows another positive correlation after 8 lag periods, which is equivalent to exactly 2 periods in the sawtooth waveform. It also shows strong negative correlation after the first half of the period of the waveform with 2 lags, and then again every half period at 6 lags and 10 lags. So this sawtooth waveform is showing strong positive correlation when the overall lag is equal to an exact number of periods in the waveform, and is showing strong negative correlation when it's equal to half periods within the waveform. In terms of its analytical value for identifying periods within the measured data, we do get some ambiguity in the autocorrelation function, in that, for example, the strong correlation after 8 lag periods could be equivalent to a waveform with a period of 4, or also for a waveform with a period of 8. So this gives ambiguity in the results. So now we will look at the partial autocorrelation function by going to time series, partial autocorrelation, and again we will choose the sawtooth waveform with 10 lag periods. But now, from this single waveform with a period of 4, we see only one response value, in that we see the first strong negative correlation has been recorded, but all the other potential correlations, the positives and other negatives, have been suppressed. So the partial autocorrelation shows a strong response after half of the period with a negative correlation, and all other correlations are suppressed. This reduces the ambiguity for the use of this in terms of analyzing an unknown waveform. So now we will look at our experimental observations of the number of porpoises observed at intervals of 3 months. So each row represents a period 3 months after the previous row. So 4 rows represents an overall time period of 1 year. If we now apply first of all the autocorrelation for the frequency of porpoise sightings, as expected, we could see strong correlations after 4 lag periods corresponding to 1 year. So there seems to be an annual variation, but because of the ambiguity in the autocorrelation, it is difficult to identify any other effects. So if we now go to Stat, Time Series, and pick out the partial autocorrelation, and for the frequency data, we now see, as expected, the response after 2 lags periods or half a year for the annual variation in the numbers of porpoises, but we can also see other possible variations, of which we can see a significant signal being outside the 5% limits. We can see a significant signal after 6 lag periods, which is equivalent to a period of 12 lags, or equivalent to about 3 years. So there, in addition to the strong annual variation, there appeared to be another variation with a period of about 3 years. And having identified this possibility, it would be useful to return to the data and possibly further measurements to investigate if this is a significant variation and if there are any possible identifiable causes.